Alright, in this video we're going to deal with a couple of problems from a recent homework assignment dealing with projectiles launched at various angles. So in this first one we have a football player kicking a ball from level ground at 25 meters per second at a 39-degree angle. So the first thing I'm always going to do in these types of problems is solve for VIX and VIY. Here I'm solving for VIX, where VIX equals VI cosine theta. Our VI is 25 meters per second and our angle is 39 degrees. So I plug in and chug and I get 19.4 meters per second as the x component of the initial velocity. Now to get the VIY, we're going to do roughly the same thing, but this time we're going to use the sine function. So we're going to use VIY equals VI sine theta, plugging in my VI of 25 meters per second and my theta of 39 degrees. I wind up with a VIY of 15.7 meters per second. Now it's also important to note here that if it was launched with an initial velocity in the y direction of 15.7 meters per second, that means if it returns back to level ground, the y component of its final velocity would be negative 15.7 meters per second. So with that in mind, we move over and start solving for hang time. We're going to use the formula average acceleration in the y direction equals change in velocity in the y direction divided by time. If we rearrange it to solve for t and expand out that delta Vy, we'll have time equals final velocity in the y direction minus initial velocity in the y direction divided by the acceleration in the y direction. Now plugging in here into my parentheses my final velocity in the y direction of negative 15.7 meters per second and my initial velocity of 15.7 meters per second, dividing it all by negative 9.81 meters per second squared, I wind up with a time of roughly 3.2 seconds. So that's our total hang time. Now there's a couple of different ways that we could solve for maximum height. I'm going to choose to use VFY squared equals VIY squared plus 2a sub y d sub y, where we know that the final velocity in the y direction, if we consider it to be the top, is 0. Now rearranging to solve for d sub y, we get d sub y equals negative VIY squared divided by 2a sub y. Now plugging in for VI sub y as 15.7 meters per second. And then if we also plug in our acceleration in the y direction, which we know to be negative 9.81 meters per second squared, we come up with a displacement in the y direction when the final velocity is 0 meters per second of 12.6 meters. So this object goes 12.6 meters up in the air. Now to figure out the range or the displacement in the x direction, I'm simply going to use the relationship where velocity equals displacement divided by time. Rearranging to solve for displacement in the x direction, I get Vix times t. Now if I plug in my initial velocity in the x direction of 19.4 meters per second and multiply it by our total hang time of 3.2 seconds, I find that my displacement in the x direction, or the range of this object, is roughly 62 meters. Now I've been kind of careless with sig figs throughout, but I'm going to leave this at 62.1 meters for now. And now I'd like to shift our focus here in a moment and go over to another question that seems very, very similar. This is number 2 from the homework. In this case, we're launching the ball with the same 25 meter per second initial speed, but at a 51-degree angle. So it's an angle complementary to that first one. So similarly to the first problem, we're going to solve for the x and y components. Plugging in our initial velocity of 25 meters per second using the cosine function, and we're taking the angle to be 51 degrees, we find that the initial velocity in the x direction winds up being 15.7 meters per second. Now, if we find the y component, we're going to be using the sine function, where VIY equals VI sine theta, and again plugging in 25 meters per second for VI and 51 degrees for theta, we wind up with a VIY of, let's see here, 19.4 meters per second. Now again, if this ball returns back to level height, we know that its final velocity in the y direction would be negative 19.4 meters per second. Now, to solve for hang time, I'm going to use the formula average acceleration in the y direction equals change in velocity in the y direction divided by time. If we rearrange that for time, we get delta Vy over a sub y. Now expanding out that delta Vy to be Vf minus Vi divided by a, and plugging in our final velocity here of negative 19.4 meters per second, then subtracting our initial velocity of 19.4 meters per second, and dividing this entire thing by negative 9.81 meters per second squared, we find that we have a total hang time in this case of roughly 3.96 seconds. So that rounds pretty closely to approximately 4 seconds, we'll call this hang time. Now, if we think about when the maximum height happens, it happens when the final velocity in the y direction is 0 meters per second. So I'm going to use vfy squared equals viy squared plus 2a sub y d sub y and cross out that vfy as 0 because again it happens when it's at the apex and the y velocity is 0. Rearranging to solve for d sub y and then plugging in the information we've already gathered, where our initial velocity in the y direction was 19.4 meters per second and our acceleration in the y direction is negative 9.81 meters per second squared, we find that our displacement in the y direction, or the maximum height, occurs at roughly 19.2 meters above the height that it was launched from. Now lastly, we're going to investigate the range. So again, I'm going to figure out the displacement in the x direction. I'm just going to use the v equals d over t equation and rearrange to solve for d sub x. So d sub x equals the initial velocity in the x direction times the total hang time. So our initial velocity in the x direction again was 15.7 meters per second, and our total hang time was about 4.0 seconds. So in this case, we find that our range winds up being roughly 62.8 meters. Now if we compare these last two problems that we've just done side by side, we notice that again they were launched with the same initial velocity and with complementary angles. So I want to point out a few things here. If we consider the 39-degree angle launch, the hang time was 3.2 seconds. But if we launch it with the same initial velocity at a higher angle of 51 degrees, we wind up with 4 seconds of hang time. Now if we consider how high up in the air it goes, if we launched initially with a 25 meter per second velocity at 39 degrees, we get 12.6 meters, and then at 51 degrees, we get 19.2 meters. Now, focus on these last two here. The ranges are nearly identical. If I had been a little bit more careful with my sig figs, they would have been exactly the same. So, complementary angles with the same initial velocity or same speed result in identical ranges. That's really important to remember.